Okay, we're going to take a look at concentration units that we use with very dilute samples. The most common is parts per million, and parts per million is simply the mass of the thing I'm interested in compared to the total mass of the sample, and this is a very small number, and so we multiply by a million. Like in weight percent, we're doing a percent, we multiply by 100, but in parts per million, we multiply by a million. And now the units of mass that we use don't matter as long as they're the same. I can use pounds of substance and pounds of sample. I can use milligrams of substance and milligrams of sample, but as long as the units are the same, they can be ounces and ounces. The parts per million is a unitless quantity. Okay, parts per million should be thought of as the number of grams of the solute, the species that I'm interested in, present in 1 million grams of the total solution if it's a liquid that we are studying the concentration of. It's very hard to think of 1 million grams of something, and so we don't want to think about 1 million grams, and what's most commonly done is to divide denominator and numerator by 1,000. So I'm going to divide the denominator by 1,000 and divide the numerator by 1,000. In the numerator, that converts grams to milligrams, the division by 1,000, and in the denominator, it takes 10 to the 6 and converts it to 10 to the 3rd grams. Now, thinking about 1,000 grams is not difficult. In fact, in an aqueous solution, if the solution is primarily water, 1,000 grams is 1 liter of solution, and that's a very typical laboratory volume to work with. So this conversion is very often done because the density of water is very close to 1 gram per milliliter. And so how many milligrams of solute are present in a liter of solution, that's really what the chemist has in their head when someone mentions parts per million. Parts per million, I want you to know, is the milligrams of solute in liters of solution. This is common to environmental scientists, to biologists. When you hear parts per million, milligrams per liter. What do we do when concentrations are very small? Well, the solution is easy. Instead of thinking of parts per million, we do parts per billion, and that is simply multiplying by 1 billion rather than 1 million. In the same way that we really want to think of parts per million as being milligrams of substance per liter of solution, parts per billion can have that same designation, but instead of milligrams, it's 1,000 times smaller, and it's the number of micrograms dissolved in a liter of solution. And finally, parts per trillion is the same thing, very teeny concentrations. The mass of substance over mass of solution is so small that we need to multiply it by 1 trillion, 10 to the 12th, in order to make the number reasonable. And in the same way that parts per billion is micrograms per liter, this is 1,000 times smaller, so parts per trillion is the number of nanograms of the substance I'm interested in every liter of solution. Legitimately, you could keep going, but nanograms per liter is, for almost all substances, the smallest detection limit that most instruments can do practically. You can do lower, but it takes quite a bit of work. So parts per trillion, nanograms per liter. Well, let's work with this new small concentration unit, and the textbook provides a good example of that in Chapter 12, Problem 123. And it gives us a lead concentration in a solution. So this is the amount of lead dissolved in 2.6 liters of water, and we want to know what the parts per million are. So anytime you're asked for concentration, write the units out, and parts per million will be milligrams of lead in liters of solution. And I just need those two pieces. You actually can see that the liters of solution will be very easy to plug in. All right, we need milligrams, and we've been given micrograms, so let's do a conversion. 192 micrograms, and the conversion is 1,000 micrograms in every milligram, and we do that division, and it's 0.192 milligrams of lead in the solution. So now let's just plug in our numbers, and 0.192 for the milligrams of lead and 2.6 for the liters of solution, and now we do the division that this ratio indicates, and the concentration of lead in the solution is 0.074 ppm lead. And the EPA will give thresholds for lead acceptabilities, and they will give them in parts per million. And you can, now one last point about parts per million, and parts per million has nothing to do with the number of moles present. I'll give you an example. If we have a solution that's 1.4 ppm lithium ions and 1.4 ppm lead ions, the number of lithium ions is not the same as the number of lead ions in this solution. If I want to know how many moles are present, I've got to divide by the molar mass. And so a 1.4 ppm lithium solution has a molar concentration of 2 times 10 to the minus fourth. Now lead has a much larger molar mass, and so dividing by that molar mass gives you 6.8 times 10 to the minus 6 molar lead in solution. And it's clear that there are many more lithium ions in 1.4 ppm lithium than there are lead ions in 1.4 ppm lead. So when people are talking about ppm, it's only the mass of material present, not the number of moles. And chemists often compare about moles. And you have to do the conversion to molarity from ppm using the molar mass.